Langevin equations with non-Gaussian thermal noise. Valid, but superfluous. In this paper, the authors tackle a fundamental question in statistical physics. Can Langevin equations incorporating non-Gaussian thermal noise faithfully represent equilibrium dynamics? This question matters because Langevin equations are central tools to model stochastic processes in many fields such as physics, chemistry, and biology. Traditionally, these equations assume Gaussian thermal noise, grounded in classical fluctuation dissipation principles that ensure detailed balance and correct equilibrium statistics. However, recent interest has grown around the possibility of extending this framework to non-Gaussian noise sources, which could arise in complex environments and lead to richer dynamics and statistics. The high-level approach of the paper is to start from a rigorous formulation of such Langevin equations with non-Gaussian noise, scrutinize their consistency with equilibrium thermodynamics, and test whether these generalizations provide any meaningful extension beyond the standard Gaussian noise approach. The authors systematically analyze the validity of these non-Gaussian noise Langevin equations, investigate whether they reproduce the correct equilibrium states, and explore the physical implications. Ultimately, they conclude these extensions are valid, but not necessary, as the Gaussian noise formulation already subsumes the required equilibrium behavior. This examination not only deepens the understanding of stochastic modeling, but also clarifies the limits and superfluity of introducing non-Gaussian thermal noise in Langevin dynamics. To conclude, the authors demonstrate that Langevin equations equipped with non-Gaussian thermal noise are indeed valid constructs from a mathematical and physical point of view, as they can be made consistent with equilibrium thermodynamics. Nonetheless, they argue that such generalizations are superfluous, because the same equilibrium properties and dynamics can be fully captured by Langevin equations with Gaussian noise, which emerge naturally from the standard fluctuation dissipation theorem. The study clarifies that while one can formulate models with complicated noise statistics, these do not lead to new or richer equilibrium phenomena beyond what the Gaussian noise formulation already provides. This insight is valuable because it streamlines the modeling toolbox for stochastic processes by emphasizing the sufficiency of classical Langevin equations with Gaussian noise. Moreover, the work helps prevent potentially misleading interpretations that non-Gaussian thermal noise might substantially alter equilibrium behavior. Overall, the paper deepens the theoretical understanding of stochastic thermodynamics, providing clear guidance on when and why complicated noise statistics matter, and when they simply don't. This clarity contributes to both the fundamental science and to practical applications where accurate yet parsimonious stochastic modeling is essential.